Zeno's paradox refers to a group of problems outlined by the Greek philosopher Zeno, who attempted to prove that all motion was logically impossible. The dichotomy paradox is built on the principle if something is a whole, it can be split in half. Suppose an individual wants to travel a certain distance, they must first reach the halfway point, then they will reach the halfway point of the remaining distance, and so on for the rest of the distance they initially wanted to travel. There will always be a distance remaining, and hence there will always be an interval to be halved. This will continue for an infinite number of steps, and take an infinite amount of time for the person to reach their destination. The individual will never reach their destination, and thus making motion or displacement from point A to point B impossible, an illusion. This is Zeno's dichotomy paradox.
Zeno speculated that since there was an infinite amount of terms summing on the right-hand side, and each of these terms were finite, this meant that the total sum of the formula was infinite. Looking at this problem through modern analysis, we can see that this is an infinite series, or a geometric series. If we multiply the series by 2, we get 1, plus 1 over 2, plus 1 over 4, and so forth. This series minus the original series equals to 1. Therefore the series for the distance travelled converges to 1. Additionally, by using the convergence test, since the common ratio of the series is 1 over 2 less than 1, this shows us that the series converges, refuting the dichotomy paradox.
The distance between any 2 points is not arbitrarily infinite when split along according to Zeno's paradox, and that this infinite series actually converges to its initial distance. So, however, Zeno conjectured that as the terms of the right-hand side are infinite, the time to complete the traversal would also be infinite. We can disprove this using the speed formula for time. So distance equals velocity times time. If your distance converges to a finite number, then you'll receive a finite number equals to velocity times time equals to a finite number. We can rearrange this as a finite number over the velocity equals the time to traverse that distance. If your velocity is standard, if it's a finite velocity, then a finite number over another finite number equals a finite number. So if your distance is finite and your velocity is finite, or not infinitely small or not infinitely large, your time to complete the traversal will also be finite, given by the speed equation, because it's a finite number will equal a finite number. If you have an infinite amount of distance to cover at a finite velocity, then you will have an infinite number over a finite number, and therefore your time to traverse this infinite distance would be infinite at a constant speed. And we can see that this holds true just intuitively.
To solve the dichotomy paradox, we can use the limit of n approaching infinity, as the series is equivalent to 1 minus 1 and 2 to the power of n. If we can take the limit of this, by applying limit laws, we can split it into two parts, the limit of 1 and the limit of 1 and 2 to the power of n. We can now solve each limit separately. The limit of 1 as n approaches infinity is just equal to 1, and the limit of 1 and 2 to the power of n can also be simplified using limit laws again. This is equal to the limit of 1 over the limit of 2 to the power of n. Then, we solve each limit separately. The numerator is equal to 1, and the denominator is equal to 2 to the power of infinity. Since 2 to the power of infinity is such a large number, we can say that it's equal to infinity. Therefore, it will be equal to 1 over infinity, which is equal to 0. Since the fraction is incredibly small, we're allowed to make this assumption. Therefore, when we combine the two limits together, we get 1 minus 0, which is just equal to 1. This shows that the dichotomy paradox is equal to 1 and not infinity.
Since we have already solved the limit of 1 minus 1 over 2 raised to n, as n approaches infinity, we now need to know whether the limit that exists is equal to 1. To prove this, we need to use the definition that for all epsilon greater than 0, there exists capital N greater than 0 such that the absolute value of the function of small n minus b is less than epsilon. For all small n greater than capital N, where the limit of the function of n as n approaches infinity is equal to b, which is quite similar to the epsilon delta definition, but instead of using delta, we use capital N because we need some large integer rather than delta, which is a very small number. To start, let's set epsilon greater than 0 and guess that capital N is equal to 1 over epsilon. So we take the absolute value of 1 over 1 minus 2 raised to n minus 1, which is equal to the absolute value of negative 1 over 2 raised to n, which is then equal to 1 over 2 raised to n. Since small n is greater than capital N and 2 raised to n is greater than n, we can say that 1 over 2 raised to n is less than 1 over n and less than 1 over capital N, which is equal to epsilon. Therefore, 1 over 2 raised to n is less than epsilon. Therefore, the limit exists and equal to 1.
Okay, was that? Oh yeah, well done, guys. Thank you. Now listen, I got to tell you that was I won't waffle because some of you are not happy about that, so I'm going to leave that. I was going to tell you an anecdote. Okay, so have we got any feedback for them, please? I thought that was very reminiscent of my earlier days studying. But who would like to make a comment, please?
I like the background music.
That's what took me back, I think. Okay, all right, well done, people. That's going to be enough for that one. All right, so.